Hello everyone, my name is Marco and I would like in this video to show you, give you a demonstration of what LabExT is, what it can do, and how we use it in our daily work in an optics laboratory. Let me give a quick introduction to the lab setup of what we're demonstrating today. On the left-hand side here, you can see the chip layout that we're measuring, the silicon-photonic chip. And on the right-hand side, you can see the camera image that the camera here on the setup, right on the right side of me, is capturing here. You can see this is the silicon-photonic chip here, and we contact it optically with two cleaved single-mode fibers. The fibers are attached to motorized piezo stages by the company SmartAct. And then we use a laser together with a manual polarization controller to feed light to the chip, and we use an optical power meter at the output of the chip to record the optical power. Our first goal now is to place the optical fibers close or at the optimum location so that we can couple as much light as possible from the fibers to the device on the silicon-photonic chip and back. I'll pull up the camera again. Here. So our goal is to move these fibers to the optimum location to couple optimally to these grating couplers on the chip. We can do this with LabExT. As a very first step, we start the live instrument view. The live instrument viewer, and make it a little bit smaller, we can choose a laser at a certain VISA address and a power meter at a certain VISA address. We can start the laser, and we can also start the power meter. And you can now see on the left-hand side, it live records of, it records in a plot of what the power meter is measuring. And now we can we could change the position of the fibers. I do this here by using the remote control of the motorized stages here to the optimum location. Now this seems quite optimum. I move now the y-axis of the left. Now I move the x-axis of the right. This seems also, oh, here we go. We get a little bit of something here in optimum. So I'm manually coupling the fibers to the device. So I'm pretty happy now. I'm pretty happy. It seems like that I hit an optimum at around minus 10.2 dB of optical loss from one fiber to the other. So now I'm happy, or even 10.1. I'm happy now, and I can go ahead and execute the measurement. So I stop the live viewer, I minimize it, and now I pull up the new single measurement button here. Now we have coupled, let's pull up to this device here. This device has ID 100. So I need to select device 100, the prototype ID 100, and now I select which algorithm I would like to execute. In this case, it is an insertion loss sweep. And I select which instruments I would like to do this insertion loss sweep with. Now I have to fix some parameters. And I would like to sweep around the C-band, so 1500 to 1590, certain wavelength stepping, and some other parameters. And I can set them here. I hit continue again, and now I save this measurement to the to-do queue. Now what I can do is I hit the 5, or I press the run button, and it will instruct the laboratory instruments to do this sweep for me. Now this insertion loss sweep is implemented according to the Keysight recommended method for swept and synchronized measurements between laser and power meter. Now we can see the sweep is done, and our measurement curve is now drawn here. On the x-axis, we have the wavelength, and on the y-axis, we have the transmission in dB from one fiber to another. Here, I can essentially select which curves I would like to plot. When double-clicking a measurement, I can see all the metadata which goes with this measurement. And I can even say, oh, no, this is an important measurement here because whatever, something that you might have observed during the measurements. When this is done, I can press save, and all your comments and the metadata is saved inside of the file which is generated after every measurement. The measurements are saved in JSON files, so they're human readable. I went now into this folder I specified as the output path in LabExT for the measurements, and I can see that the measurement data have been put into a JSON file here. When opening the JSON file, you can see that it's actually human readable, structured code. Every modern programming language allows you now to do post-processing on the measurements. The file starts with a couple of metadata, and also, for example, the measurement settings used, but also then the measurement vectors. So of the vectors that we see plotted in LabExT before. Now we have seen how a single measurement can be executed using LabExT. But now take, for example, this prototype chip here. It contains a couple of tens of prototype devices that we would like to measure exactly as we did before. So as a first help, if you enable the motorized stages in LabExT, LabExT can execute the so-called search for peak. So it will adjust automatically the position of the fibers, the X and Y position of both fibers, to maximize the optical throughput from one fiber to another. And I do this by opening the search for peak window here. Now it allows me to set which laser and power meter that I would like to use, and also some search for peak parameters. After it's done, the optimization is displayed in the search for peak window here. You can see for the X and Y dimension of the left stage and the right stage, the fibers were moved to different locations and the optical power recorded. The software then fitted a Gaussian shape and identified the maximum point of this Gaussian shape. It then moved the fiber to this optimum location for coupling. Okay, so but this is just one step that LabExT is able to do. Say we want now to measure a couple of the devices. I would like to measure this one, this one, this one, this one, and I believe this one and this one. So let's actually automate this. I do this by clicking New Device Sweep Experiment, and I mark by essentially marking and then hitting this button over here, the respective IDs. I prepared this, of course, for the video. So I've prepared device, these two, and also these two devices. I press continue. So on all these prototype devices, I would like to execute the insertion loss sweep. I hit continue. I again select the laser and the power meter that I attached to our measurement setup. And then I will have to fix the parameters. These look very good to me. So I hit OK. And finally, I click continue. And now you can see that LabExT has added many to-dos. So now we are set up and we can hit run. I will pull up the camera, and now the LabExT has moved the fibers to the position of ID. Let's look at it. Here, this is the to-do list ID 100. Now it executes a search for peak as we've seen before. You can also look at the search for peak curves here. Okay, now not now, but in the next throughput, we'll have the camera here again, and now it does the measurement. Now the measurement curve popped up, and it moves to the next device, which is 101. It does a search for peak. So this is shown here. This is X dimension, the left stage, Y dimension of the left stage, optimizes the position of the fibers, and it does this for the other measurement, for the other stage as well. Now it executes the measurement again, and we will see the measurement curve appearing very shortly. So LabExT has finished executing automatically the measurements for all the prototype devices. We have acquired all the insertion loss curves of the selected device prototypes. So, and that's how you automate multiple device scans with LabExT. So to wrap up this video, I would like to give you again an overview of what I've shown. LabExT provides you with a very easy way to define a measurement routine and to execute it with desired laboratory instruments, and then to save the resulting data in JSON files. I would like to thank all the co-authors, the so far co-authors of the software, and of course my employer, the Institute of Electromagnetic Fields at ETH Zurich, and also Polariton Technologies, which co-sponsor the public development of LabExT. Here I have copied you again the links to go on GitHub to find the source code. We can also go onto readthedocs.io, labext.readthedocs.io to find the online documentation. There you will find an installation and a configuration guide of what we haven't shown you here today in the video, but also essentially a how-to for a new SWEP signal measurement. So with that, thank you very much for watching and have fun using LabExT and automating your lab work.